Can I go?
Yeah. So the next talk will be given by Elena Celedoni from Norway and TNU on the talk is about deep learning as optimal control problem on structure preserving deep learning. Elena?
Yes. Thank you again, Frederick. So this talk is about deep learning as optimal control and structure preserving deep learning. I've been working on this subject on a couple of papers recently with a number of collaborators, and you see the names listed here. And I also will mention some work that I've done longer time ago in 2004 together with Simone Fiori. So what we are interested in is somewhat to understand a bit more the mathematics behind deep learning. And also my background is in structure preserving integrators and numerical geometric integration. And so we are interested to see what geometric integration can do for problems in deep learning. So the talk is divided in 3 parts. The first part is about, say, the first paper listed here is deep learning as optimal control. And the second part is extracted from the paper number 2. And so is the third part, at least to a large extent. But to the very end, I will mention the connection to the last paper. Okay, so let me start. I will start with an introduction. I hope I'm not offending anybody by taking it up. It's more a setup of the notation that I'm using than anything else. So we are considering artificial neural networks, which are often depicted in the following, with the following structure, the following diagrams. And mathematically, one could say that these are a composition of maps, phi 0, phi 1 to phi L, up to phi n minus 1, n minus 1 of such maps, where the phi 0 is processing the input y in, and phi n minus 1 is delivering the output y n out. So, so in a shorter version, we can say that the layer number L in the network is mapped to the layer number L plus 1. So the input number L is mapped to the output YL plus 1 by the map phi L. And phi L is a map that has the following structure, is always the same phi for each L, apart from the parameters UL here, which are different at different layers. Okay, what is learning? Learning is a process where we impose a cost function on the network. Typically, this cost function is depending only on the output parameter, on the output of the network, and not on the preceding values. And this output will depend, will range on all possible outputs that are obtained by starting from an input in some data set. And we optimize with respect to the parameters over all the layers. So we can think that the input belongs to a large database of images. For example, this is a typical example. But and we want to optimize over all these parameters, and we use typically stochastic gradient descent for optimizing. Uh, okay. So what else wanted I want? Um, Deep learning has to do with the number of layers. So when n is large, capital N is large, we're talking about deep learning. And what is known is that training deep neural networks, so when n is large, is much more difficult to solve these optimization problems. So here is an example taken from a paper from 2016. This is not a very old paper, but still is rather old in the deep learning, machine learning community, you can say, because something appeared 4 years ago is ancient history in deep learning. But what you can see here is the comparison of two different architectures. The left-hand side, we have a plain network, feed-forward neural network architecture. And on the right-hand side, we have the so-called ResNet. And as you can see in the left-hand side, we have the convergence history of the optimization algorithm. And the red line is for 34 layer, for a 34 layer networks, and the light blue line is for 18 layers. And the one for 18 layers achieves lower error than the one for 34 layers. So adding layers in the neural network, it doesn't improve the performance. On the other hand, on the right-hand side, we see that this is not the case, that the ResNet is able to obtain better performance with 34 layers than with 18 layers. And mind you, 34 layers means that we have many more parameters to learn, so that the optimization is more difficult, but also what we can obtain with our network is the network is much more powerful. So we would expect to obtain a better error with 34 layers than with 18 layers, but it's not so straightforward as one could imagine. So adding layers does not always decrease the error. Deep learning can lead to vanishing and exploding gradients. Vanishing gradient, you can see here that there are flat areas in this convergence history of the two graphs. So the gradients are almost zero, but still after a while we see that the gradient drops. So there is improvement to be made still in the convergence. And it's obvious that the ResNet architecture works better than the plain feed-forward architecture. Okay. So let's stick to ResNet since it works better. And let me explain a little bit more of details about ResNet. What's the map that is sending layer L to layer L plus 1 in ResNet as the following format is taking the previous layer YL and adding some correction. And this correction is nonlinear one. It depends on the parameters UL. And the parameters UL are typically given by a matrix which will multiply the input YL and the vector which will be added to this product. F is called the residual function, and typically there is, as I said, a linear interaction between the parameters and the data or the input, and there is a scalar nonlinearity which is applied components-wise. This is very special, but it has big advantages when it comes to the computational cost of the algorithms. So a slight modification to the ResNet is made by introducing a scalar parameter HL HL here. So of course, which with HL constant equal to 1, we get back to the previous situation. So let me allow me to do this slight modification for the time being. When it comes to the cost function, I have to mention something here. The cost function is typically given as a sum of contributions over all data. So it will be, it will have a format as you can see here at the end, at the bottom of the slide. This means that also when we compute gradients with respect to the parameters, we can do it, it will be, the gradient will be a similar sum of gradients of each of the contributions. And this is very important for the implementation in terms of stochastic gradient descent. And this was mentioned already yesterday in the first talk of the conference. Because in those cases, instead of computing the gradient by considering altogether all the contributions of the data, you just select some subset of the data and you compute gradients only with respect to that subset. So you make update or gradient descent algorithms that take into consideration only a subset of the data at each iteration. And this saves a lot of calculations, and this makes the algorithms much more efficient or cheap. Okay, let me summarize. Then we have our input data, which is coming from a large data set. N, capital N is the number of layer, and capital N is the number of the output layer. We have parameters, one for each, or set of parameters, one for each layer. And we have a cost function, which is made of a sum over all data. Then the deep learning problem for ResNet can be stated in 2 lines as follows. It's a minimization problem over all parameters of the cost function, subject to the following constraints, which you can see here at the bottom of the page. So first observation is that this constraint here, YL plus 1 is equal to YL plus HL times F, can be thought of as the discretization of an ODE by a forward Euler method. So forward Euler discretization of Y dot is equal to F of Y and U. And here, as before the step size was taken equal to HL, but now you see that in this forward Euler interpretation of the problem, we have used for this parameter HL because it becomes the step size of integration of this forward Euler discretization. Okay, so now we are ready to state the optimal control formulation of the problem. So it was proposed more or less simultaneously in 2 papers, or at least by 2 groups, one led by Haber and Rutotter in Canada, and one in the United States led by Wayne and E. And both groups have worked a lot on this formulation later on. And as you can see, the previous pink box can be thought of as a discretization of a continuous optimal control problem, which is stated here in the equations 1 and 2. So what is the advantage of this optimal control formulation? Why should we look at it in this way? Well, it's a simplification of the problem. It states the problem in 2 lines. It can be used to create new architectures, and definitely there has been many people who are doing this exercise already. It's a continuous model, so it could be a simpler way of looking at the problem, and it offers a starting point for analysis. So um, not a big surprise, in fact, that there are a lot of people who have been working on this point of view of optimal control for deep learning. And here's a number of references, and this is not a complete list, as you can imagine. And all of this is quite recent, starting from 2017, and the last references is 2020. Okay. So let me say just a few words about our contribution. What did we do? Very quickly, perhaps it's not so important to state what we did, but let me say it anyway. So our background is background of people in optimization and people in numerical analysis of differential equations. And what we wanted to see was what can we do with our background, starting from this optimal control viewpoint. What is known, what are the usual numerical methods that are used for the discretization of optimal control problems, especially if your starting point is Euler method, what can you do with other Runge-Kutta methods? So we essentially apply theory which is quite well known in numerical analysis for optimal control. We apply it in this setting of deep learning. We derive explicit formulae for the gradients, and we implement a range of Runge-Kutta discretizations and make comparisons. The codes are available on the internet and on GitHub. And we also obtain some nice results regarding the learning the step size. So we optimize also with respect to the step size and see what happens. Okay, let me review some of this work. First thing one has to remind oneself is that the optimal control problem is strictly related to a boundary value problem. A system of Hamiltonian system, boundary value problem of this format, which is given by these equations, which express the first order necessary conditions for optimality of the optimal control problem. Here the Hamiltonian is given like so, it's very simple, and this is an differential index 1 differential algebraic equation because of the constraint which comes from differentiating with respect to the parameters u. So the typical methods for solving these problems, typical numerical methods for solving these problems are symplectic Runge-Kutta methods, partitioned Runge-Kutta methods. And why is that so? The reason is the following result. I will state it in form of a theorem in the next slide, but here is a schematic version of it, which is as follows. Suppose you have an optimal control problem on top here, and you optimize, so you derive first order optimality conditions, then you obtain this nice Hamiltonian boundary value problem. Suppose then you discretize this system with the symplectic partition Runge-Kutta method, then what you obtain is the same as if you had discretized your optimal control problem by the first of the two Runge-Kutta methods, phi L here, and then you had optimized. So the commutativity of this diagram here, discretize, optimize, and optimize, discretize, is obtained provided you solve your boundary value problem with a symplectic partition Runge-Kutta method, which means that you apply one method for the first equation for y here, and you apply a companion or an adjoint method for the equation for p. So here is the same result stated for the couple forward Euler backward Euler. So if you discretize the boundary value problem with a forward Euler for the first equation and a backward Euler for the second equation, this is a symplectic discretization partition Runge-Kutta method, symplectic Euler method discretization of this problem. Then what you obtain is the discrete, the optimality, the first order optimality, necessary condition for optimality for the discrete optimal control problem. And this is stated for the forward Euler, backward Euler pair, but it's a result that is valid for any symplectic partition Runge-Kutta method. As another interesting side effect, you get explicit formulas for the gradients. So here, what this tells you in some sense is the formulas for the back propagation. So if you have chosen your favorite method for doing the forward propagation, then the back propagation of the neural network is given automatically by, in this case, the backward Euler, but you can say by a special Runge-Kutta method that you can compute out of the coefficients of the starting Runge-Kutta method. But you have also explicit formulas for the gradients with respect to the parameters. And never mind these complicated formulas here. They are based on the Runge-Kutta parameters as well. And what's interesting is that you can write them down explicitly without needing to using automatic differentiation. Okay, so how is the algorithm? The algorithm is works as follows. You have your forward propagation here. Again, the example is the forward Euler, but you could use your favorite explicit Runge-Kutta method. Then you have the backward propagation with the companion method, which I don't state here, but it's just can be written down from the coefficients of the forward propagation method. And then you have your formulas for the gradients that you can use to update the gradients. And when you have that, you can use the gradients to update your gradient descent iteration, as you see at the bottom of the slide. So all this is simply an application of theory which is well known. In particular, there was a paper by Heger from the year 2000 where he was analyzing the use of Runge-Kutta methods in optimal control, and in particular he proved convergence of order P for Runge-Kutta methods, provided they were essentially symplectic partition Runge-Kutta method applied to the boundary value, Hamiltonian boundary value problem. So he analyzed all this and analyzed convergence as well in his paper. But he didn't discover the connection with symplectic Runge-Kutta method. He just did it without knowing that these were exactly the symplectic Runge-Kutta methods. And this connection was pointed out later on by several authors. Among others, there is a review paper by Sanserna from 2015. Recently, Thorpe and Genip studied deep limits of, as n goes to infinity, the number of layers goes to infinity in the context of ResNet. And they used techniques from gamma convergence. But it's not clear yet how the theory of Hegel, the theory of convergence of Hegel, can be adapted in the case of deep learning. And it could be an interesting project to look at this. Okay, what I'm going to do next is to show some simulations. And we've been using, I don't know if this is viewable, I hope so. We've been using simple test cases. We also did some tests, more interesting tests, but we believe that these simple test cases are quite interesting if you are interested, more interested in the mathematics behind the problem than in the performance of the algorithms. So just a few more words. Again, my setting here, the nonlinearity sigma, as I said, is a scalar function, and it's in the experiments is the hyperbolic tangent. But also later on in some of the analysis, I will consider the ReLU function, which is this max of 0 and C here. And just a little bit more on the structure of the optimization of the cost function, which is a typical cost function for deep learning. And here C is this again scalar function which is applied component-wise. K out and B out are the parameters, the matrix and the vector parameters of the last layer, and they will have the right dimension so that they match the vector C in here, which is describing the truth about the data. Okay, so here are some pictures. Every column here is a different Riley-Kutta method. We start with the Euler method, so the ResNet. Then we go up with order 2, 3, and 4 in particular. The first row with this spiral data, and we want to separate the red points from the blue points. And the background is red, where the prediction is that there should be red points, and the background is blue, where the prediction says that there should be blue points. So in the bottom line, what you see instead is the result of the separation, so how the points have been evolved and separated from throughout the process by the learned parameters. Here you see again, each row is a different method, and you see the evolution of the data throughout the network and how the data is separated in different times. So the first row is again the ResNet, and then order 2 Riley-Kutta method, 3 and 4. And we were kind of sorry to say or to see that there were no big differences in between the different methods. Perhaps there is a slight difference in between the order 1 method and the order 2 and above, but above order 2 they seem to behave all in a similar way. Still, it was interesting to see that there was this consistency in the various methods. If you want to look at more pictures, there are plenty of the simulations in the paper. Here is something I have to, these experiments, I have to acknowledge the help of Brynjulf Overen in particular, and in the next slide, these experiments have been done by Matthias Herrart. So what we're comparing here is the feed-forward neural network. We see there is a much bigger difference in between the different results. Every column is a different method, and the first one is a simple feed-forward neural network. The second one is ResNet. The third one is ResNet, but we have been learning the step size. And the last one is, again, with learned step size, but we also have a constraint on the step size. The final time is t equal to 1, and the sum of the step sizes is equal to 1, and they're all positive. While in the previous case, in the third column, the step sizes are allowed to be negative. So as you can see, there is now a big difference in the different methods. In particular, the feed-forward method is not performing very well. It's not predicting very well. It's not performing very well. And the three other ones are different, are performing differently. In particular, the last one is having a very irregular convergence. But still, it's achieving the goal, the optimization or the separation goal in very few steps. Okay. So here is a slide of summary of what I've said so far, but in the interest of time, and since you are going to dinner in not so long, I think I will skip this slide. What I want to say now is to say a few words about the stability of the forward propagation. So what the setting is as follows. We are assuming that the optimization is already made, and we have found U of t. This is an idealized situation in which we are solving exactly the optimal control problem, and we find the U of t, the parameters. The parameters are again divided into a matrix A of t and a vector B of t. Then we ask what are the properties that we would like to have from the vector field F that propagates the data. What structural properties should F have? Well, one desirable property is that nearby solutions remain close to each other. So if we start close to each other, we don't want to the solutions of the forward propagation to depart from each other too much. So we would like C here to be a constant. Of course, if F is Lipschitz, we know that C is e to the TL, where L is the Lipschitz constant. And the Lipschitz constant for our vector field, which is given here as this format, as I mentioned before, will be the product of L sigma, the Lipschitz constant for sigma, times the maximum of the norm over T of A of T, the matrix of parameters. Okay, it has been argued by Aber and Rutotto that one could look at the eigenvalues of the linearized ODE to analyze the stability of the problem. This is definitely a good idea in case the parameters are not varying too much. So if you can say that A of T and B of T are smooth and very, very slowly, then this analysis can be a good idea. However, this is not always the case. And then perhaps other means of stability can be considered. For example, Lyapunov stability. And I can mention that already in the 80s, Hopfield's networks were built in such a way that the propagation would have a Lyapunov function, non-increasing or constant along the solution trajectories. What we have been considering is instead the property of contractility in the L2 norm. And we have been using a one-sided Lipschitz concept. This is very typical in numerical analysis of ODEs. It's used for studying stability of integration methods for ODEs. So what we are assuming is that the vector field F is satisfying this property here. So there is in the L2 inner product, we have this inequality, and mu here can be negative. So we have a Gromval-like inequality for the solution, but when mu is negative, this is really contracting the solution. So, so this is the case which is interesting to us. So for our vector field in the context of neural networks, one can estimate the new constant by means of the supremum over T and D of the maximum eigenvalue of the symmetric part of the matrix D times A. A is the matrix of parameters, and D is a diagonal matrix which is related to the nonlinearity sigma, in particular to the first derivative of the nonlinearity. Zhang and Schaeffer very recently have made a study of stability in the case sigma is ReLU, is the ReLU function, and for a vector field F that has this format over here. So it's not exactly the usual vector field that I've been considering so far, because it has an extra matrix A here in front, A2, which pre-multiplies the whole thing, and two bias vectors. So we simplify these situations just a little bit, and we consider this that A2 is equal to A1 is equal to A of t, and the vector field has this format. This vector field is a gradient system in the following sense, that y dot is equal to the minus the gradient of v with respect to y, but v is depending both on t and y, so it's non-autonomous in this case, and in particular it has this format here. It's a function gamma applied to the vector a of t times y plus b multiplied with the vector of ones, so summing up all the components. And gamma is here nothing but the integral of sigma. So in this, for this kind of vector fields, we can prove the following theorem, which is indeed similar to the results that can be found in the paper by Zhang and Schaeffer. And first of all, given that V is twice differentiable and convex, we can always show that there is a one-sided Lipschitz constant with nu less than or equal to 0. And moreover, we can say that this nu is not too negative, because when nu is very negative, this can be too much contractivity. So we have a lower bound for the value of nu, which is given by the smallest, the minimum over t, the smallest singular value of the matrix A of t of parameters. So too much contractivity can be a disadvantage, and therefore sometimes it has been proposed to replace this vector field F with a Hamiltonian vector field. But typically this Hamiltonian vector field becomes non-autonomous. And although I've been hearing about numerical methods for non-autonomous Hamiltonian vector fields, I still think this field is not very well understood yet, at least not for those who are not expert in the field, and there is still it's not so clear what one can get by using Hamiltonian vector fields. But certainly, there are experiments that show the performance of problems where f is a instead of being like this, like a gradient vector field, is a Hamiltonian vector field. But I'm not going to mention this or to discuss this very much in this talk. When it comes to discretization, so we have seen here the properties of the vector field. So say that we now want to implement this and we want to discretize this with Runge-Kutta methods, then one option is to use B-stable Runge-Kutta methods. These are contractive methods, and they are contractive independently on the choice of the step size. So independently on the number of layers. However, these methods are implicit, are all implicit. So it's more interesting in the context of deep learning, the way typically this is implemented, to look at explicit methods. And then there is a seminal work of Dahlquist from the 70s, which explains everything about explicit Runge-Kutta methods and contractivity. And in particular, if the weights of your Runge-Kutta method are all positive, then you have the following bound for the step size here. So the step size, as long as the step size is less than a certain constant, which is here related to this new bar constant, which satisfies this equation, which has to do with the problem or the vector field that you are considering, and is depending also on another constant r here, which is depending on the method that you're using. In particular, for the Euler method and for the Runge-Kutta 4 method, this r is equal to 1, so one has not to worry about it. Then, provided h is smaller than this constant here, you have contractivity. Okay, now I've come to the last part of my talk, which is about iterative methods for training the networks. I'll start with this slide, which shows a comparison of different iterative methods. Typically, in this field, the iterative methods which are considered for training the network are gradient-based. So as I showed you in the beginning of the talk, we are able with the techniques, for example, with the method, with the ResNet architecture, to compute the gradients with respect to the parameters. And then when we have the gradients, we can make a gradient descent iteration in order to improve upon those parameters. So that's the typical situation. And another thing which is very important with gradient-based algorithm is that they can be implemented in a stochastic gradient fashion, with the advantages about computational cost that I was mentioning and that were mentioned yesterday as well. So gradient-based, it's important. And accelerated gradient is another category of methods which are used in this case. So here you see a number of these methods. The first one, the blue one, is the gradient descent, the usual gradient descent, and the others are all Hamiltonian descent or accelerated gradient descent type of methods, which are based on second-order equations. And the most popular of all is definitely this Adam method, which is really performing quite well in a number of situations. And here you see it's also the one which is performing the best in this very simple 2D optimization problem, which is a typical problem, test problem in optimization for testing algorithms. So the other methods are all based on second order equations, while the GD is based, of course, on first order equations. And there are a number of them which I will discuss later. Okay, so so as I said, first order equation, gradient descent is based on this ODE, U dot is equal to minus the gradient of the objective function, of the cost function. And instead, Hamiltonian descent or second order or accelerated gradient descent is typically based on systems which are of Hamiltonian type, and which look as you can see here at the top of the page. They are Hamiltonian system with linear dissipation, and they can, in this example here, it can be written also as a second order ODE with the gradient on the right hand side. So based on this set of equations, if you use a normal method for discretizing the first equation and the implicit Euler method for discretizing the second equation, then you obtain a very famous method which is called the Polyak heavy ball method, or gradient descent accelerated by momentum. And as I said, it's a forward Euler, backward Euler discretization. It's the same discretization that that I described also earlier in connection with the optimal control problem. So this is a particular example. This ODE up here, or this ODE system, is a particular example of a conformal Hamiltonian system. So Hamiltonian system with Hamiltonian H with linear dissipation. Here, what we're going to choose, we are going to use is a simple kinetic energy for this Hamiltonian system, which is just the norm, the scaled norm of the momentum. But other choices are possible. For example, this K of P equal to the square root of the norm square of P plus epsilon, which leads to something which is called relativistic gradient descent, which is closer to the very popular Adam method. Okay, some properties of these conformal Hamiltonian systems. So the main property is that instead of preserving the symplectic structure, they are contracting the symplectic structure by a certain amount, which is given by an exponential of minus gamma t. So the symplectic structure is contracted by e to the minus gamma t. Moreover, the energy is dissipated, and it's easy to prove. They converge to a stationary point, provided the J is bounded below and H is radially unbounded, which is typically chosen in this way in the context of deep learning. And the limit points of the conformal Hamiltonian system recover the stationary points of the objective function, or sorry, of the cost function J of u that you want to minimize. The thing is that when you have a system like this, the typical discretization of this system, or the geometric, the one discretization that preserves the most important properties of the system, is the conformal symplectic discretization. And I'm not going to say a lot about this, but I can just tell you that the Polyak heavy ball method with the symplectic Euler discretization of the system is exactly a conformal Hamiltonian discretization, or conformal symplectic discretization of the conformal Hamiltonian system that you see on top of the page. Another example is this nested of accelerated gradient, which is nothing but a discretization of this system after a change of variables, which you can see here perhaps at the bottom of the page, where you first change the variables p into p tilde, where p tilde is the exponential of gamma t. And then you apply another symplectic integrator, which is the Stormer-Verlet method. Next is the relativistic gradient descent. Here you change the kinetic energy, as I told you before. It's again kinetic energy which is suitable for the problem. And then you apply the symplectic Euler discretization to the problem. Okay, so why is it interesting to look at ODEs that are related to these methods, to these iterative methods? The reason is that they are useful to prove convergence properties, for example, and this is very much the case of the nested of accelerated gradient method, which there is a popular paper by Su, Boyd, and Candes, as you can read at the bottom of the slide, where they study the properties of convergence of the nested of accelerated gradient by means of by studying the ODEs which are underlying this method. And you can use them to improve the iterative methods by, for example, by discretizing the ODEs with different or better methods. And you can use them also to generalize the methods to the setting of manifolds, for example, or of Riemannian manifolds. Here I have a number of references for conformal Hamiltonian system, both for theory and for numerical discretization, which are relevant in this case, while the last part of the slide is dedicated to references in the deep learning or Hamiltonian descent learning literature. Okay, the very last part of my talk is about generalizing these ideas to Stiffened manifolds and to orthogonality constraints. So the Stiffened manifold, I will focus on that simply, is a manifold of matrices n times p, where n is larger than p, often very much larger, and with orthonormal columns. These matrices have orthonormal columns. So in particular, when n is equal to p, this will be orthonormal, so orthogonal matrices, so they will belong to the orthogonal group. Why are orthogonality constraints interesting in the context of deep learning? Well, the reason is that to impose constraints on the parameters, matrices of parameters in deep learning, it has been shown to have good effect of regularization. So it improves the speed of and the efficiency of the training, and it regularizes the problem. You can find applications of this in the literature for blind source separation, independent component analysis of signals, and also in convolutional neural networks. Okay. One interesting system of equation that Simone Fiori proposed a number of years ago was this Hamiltonian flow with dissipation on the Stiffened manifold. It's he was considering a one-layer neural network with input x and output y, and U here is a matrix of parameters that belong to the Stiffened manifold. And in order to optimize the cost function j, he proposes this system here, which is exactly a Hamiltonian flow with dissipation, with linear dissipation. It is possible to show that this system is exactly of the same type as the Hamiltonian systems seen earlier in the not in the context of manifolds, and has this format here. So also this old algorithm based on this set of equation is belonging to the same class of problems. Okay, in this last slide, I want to mention that we have done some work on gradient descent on manifolds. So, provided that the parameters of the learning parameters are belonging to a manifold, and this manifold is endowed with a Riemannian metric. This, I think, was mentioned, for example, yesterday by Alexandro Bart. So one could use methods which are adapted to manifolds. In particular, discrete gradient methods on manifolds are those who guarantee the descent at each iteration. There is one particular one which is based on the Ito-Habe discrete gradient, which I presented last year at the GSI conference, which is particularly interesting because it's relatively cheap. It's quite cheap to implement. And the last part of the slide here, you see a number of references. First, the reference to Simone Fiore. He has a number of papers on this method, both the system and the numerical discretization. We worked together on an improvement of the numerical discretization based on Lie group integrators. And also very recently, it appeared in a conference proceedings, a paper on the generation of the Adam method on Stiefel manifold. And then I want to mention this last paper here by Lehmkuhler and Patrick on symplectic integration on Riemannian manifolds, which could be also useful for adapting methods in this situation. Okay, this is everything I wanted to say. I thank you very much for your attention and to keep up with this Zoom presentation. Thank you very much. Thank you, Frederic.
Questions? I will, because the microphone is on my laptop, so it's not so easy.
Elena, do you hear me? Do you hear me, Elena?
I kind of hear you.
The logistic is not very good.
Okay, hopefully you hear me now.
Oh, okay. Zarko.
Oh, yeah.
Hi.
Nice to see you again.
Nice to see you.
You mentioned Stormer-Ferré scheme and also Lie group schemes, and as you, of course, you know, those schemes that preserve intervals of motion. And so, does this feature, for example, you mentioned Stormer-Ferré, does this feature actually give benefit in your setting?
I think that you have to adapt it to the manifold setting if you want to preserve for example, the orthogonality constraints. So, but for example, orthogonality constraints are typically preserved by the midpoint rule. So if you are willing to use implicit methods, then you might be willing to try the midpoint rule. But this is not typically done in the context of deep learning, because typically you want to instead use explicit methods because it's because of costs, computational cost. You don't want to afford to solve nonlinear systems of equation of large dimension.
Other
This
question?
is my understanding of the situation.
Other question? I have one, Elena. One challenge in neural networks is to reduce the number of layers on parameters. So some people are working on topological gradients to optimize the structure of the layers. So the number of layers, the number of parameters. There's a good property also because when you have a parsimonious network, you will regularize your solution because you have less parameters, so less degree of freedom. Do you work on this direction to try also to optimize the structure of the network?
I think it's quite difficult to understand these sort of things, these sort of questions. So, for example, in our experiment that I showed earlier, the ones with the variable step size, this one, this last column here, you really have you get to the target in very few steps. But these steps are very regular. So if you look at the flow or how the configuration of the points is changing throughout the time, with time, you see that it's changing very erratically. It's not regular at all. On the other hand, you might argue that for stability reasons, if you have a large number of steps in your time integrator, so a large number of parameters as well, then the whole thing becomes more regular and not more irregular. But I understand what you're saying, that you don't want to have overfitting, you don't want to have too many parameters in your network. And that's why perhaps the orthogonality constraints or other form for constraints could be a good idea. So this connection of deep neural networks and few parameters and how to manage the whole thing, how to balance the whole thing is not that simple, in my opinion.
Okay.
But I would go for the constraints, for imposing constraints, appropriate constraints on the matrices of parameters.
Yes, because many parameters means also many data. So if you want to learn with a frugal data set, you have also this constraint. Okay, no more questions?
Sure.
Okay, so thank you, Elena. Thank you for your talk.
Thank you, Frederick.
See you soon.
Thank you very much. Have a nice dinner.